Hey guys, welcome to my channel, and in this video we're going to talk about wind. Okay, so wind is basically the movement of air, and air is the composition of gases, and these gases are held down by gravity, and that's what's going to form Earth's atmosphere. All right, excuse me. So that's going to lead into our first topic, which is pressure. Okay, more specifically air pressure, scientifically known as atmospheric pressure. All right. So as I mentioned earlier, air is comprised of a bunch of gases, right? And gases are basically invisible to the naked eye. So what we're going to do is we're going to have these red dots be our representation for gas molecules, okay? And we're just going to pretend they're in some sort of confined space, okay? They're not in outer space because there's no air in space, but they're just in some sort of confined space that's on Earth, let's say. Okay? And as you can see, they just kind of float around and move, and they're just being gas molecules. Okay, so that's basically what they do. They just float around and move around. All right. What we're going to do with this space is we're going to play with the temperature. So the first thing we're going to do is lower the temperature. All right. And what's going to happen is the gas molecules are going to contract, pull together, become more dense, and they're also going to have trouble moving as much. So you can see that their movement has been a bit nullified. And so as they become more dense, more pulled together and everything, what happens is this actually becomes a high air pressure situation, because that's the characteristic of high pressure. Gas molecules are just pulled close together, right? And they're kind of heavy. Now what we're going to do is we're going to heat up the room. So it's going to get hotter, and the gas molecules will now begin to expand and push each other away. And they've gained all this energy all of a sudden, making them want to move a lot, right? That's because they feel lighter and they're less dense, right? And since they're more spread apart, this can technically be considered a low pressure situation. Alright, so now what we're going to do is we're going to go ahead and stop playing with the temperature. Okay, and the gas molecules will go back to their normal state as earlier. I want to point out that temperature is not technically a metric of affecting, not the sole metric of affecting the air pressure of an area, right? So what we're going to do now is we're going to add gravity. Okay, so what Earth's gravity does is anything with mass gets pulled down by Earth's gravity. So even gas molecules have mass, right? And what happens now is that area where they're all pulled down to, all the gas molecules, becomes a high pressure area. Okay, and the area with no gases is low pressure, because it fits the description, right? When the gas molecules are more close together, contracted together, high pressure. More spread apart or non-existent, low pressure. Okay, but this time we're going to also play with the temperature again, but we're going to make one side hot and one side cold. Okay, so the gas molecules will react accordingly. The hotter ones will expand and push away. The colder ones will kind of pull together. Okay, and I want to point out, you have to pretend that they're moving like earlier, so you have to remember that hot gas molecules move, cold gas molecules do not as much anyway. And in this situation you also saw there was a change in the air pressure, right? So low pressure, high pressure has moved to completely to the cold side. So what happens is also the density is affected. So hot gases are less dense and cold gases are more dense. And another thing is, since we have gravity playing a part this time, the cold gas molecules, since they're unable to move, they just get pulled down by gravity, right? So that means only the hot gas molecules are able to move as much and as freely. So what happens is they keep expanding and expanding and expanding, and what they do is they move into more space because they need more space to move. So that's like hot is hot and cold is cold. But that's the best I can explain it. Anyway, so you see another change in the air pressures, right? The hot gas molecules start invading the cold gas molecules space, because that's the only area they can move into. There's no more space in the hot side. And what they do is they start pushing. What happened? Hey, again, sorry about that. I had some technical difficulty, but I think I fixed it. So as I mentioned earlier, the hot gas molecules will invade the space of the cold gas molecules and push them out. Since the cold gas molecules aren't able to move, they have no choice but to get pushed out of their space, and the hot gas molecules will just keep continuing into their conquering of the colder space. But what happens now is the once cold gas molecules will begin to warm up, and the once warm gas molecules will begin to cool down. And this is going to create a circle of life for the gas molecules. And you see here that it basically just repeats itself, but with the other gas molecules in play. Okay, so let's go ahead and stop playing with the temperature. And there, so we're back in our normal state. So as I mentioned earlier, temperature alone does not play an effect on whether an area will be low or high pressure, right? I want to point out also that not all gas molecules are as dense as the ones that I've shown here. Some gas molecules are actually light enough, even in a normal temperature setting, that they're able to float up into higher points of the atmosphere. Okay, so the only thing that holds them back from going into space, though, is Earth's gravity. Right. So next thing we're going to talk about is we're going to go into space. So this time we're actually in space, and we're going to talk about the rotation and revolution of Earth. Okay, so this is a top view of the Earth and the Sun, and the Earth, to make a full rotation, so each day the Earth makes one full rotation, so that's equivalent to about 24 hours. Okay, and it does one whole revolution around the Sun every 365 days, right? So the Earth rotates eastwardly, and it goes around the Sun counterclockwise. 24 hours, 365 days a year, approximately. And that's the end of that topic. Let's go ahead and zoom in, and this time we're going to talk about the next topic, the Coriolis effect. So this one is a bit difficult to comprehend. I want to point out again, the left side is east and the right side is west. This is because we're viewing the top of the Earth. Okay, so we always have to know what direction we're facing. Okay, so I want you guys to pretend that you're just standing somewhere in Asia in this scenario. Okay, and the Earth is just rotating eastward. So as the Earth rotates, you move along with it. So even though you're not moving, the Earth's rotation in effect makes you move. Okay. Next scenario, I want you to pretend that you're walking along with Earth's rotation. Okay. So what happens in this scenario is, compared to when you were standing, you start moving with Earth's rotation. You're actually moving more faster than you think you are. You're moving faster than you think you are. That's because the Earth is rotating. So you're moving fast enough to walk on water, apparently. But yeah, so the Earth is rotating, which means that even though you think you're just moving forward, because of the Earth's rotation, you're moving much faster than you think you are. And again, let's pretend that you're walking the other way. As you walk the other way, since the Earth is still rotating, you're actually still moving the same direction as the Earth is, unless you walk fast enough that you counter its rotation. So technically, you're moving the same direction even if you're standing still. You're just moving at a slower pace because you're moving against it. So you need to move fast enough to go against the Earth's rotation. Okay, and this time I want you to pretend that you're a superhero that can fly. And this time what you're going to do is you're just going to fly straight up. Okay, so as you start flying straight up, what happens is you start falling behind from if you were just to stand still. And this is because the only thing that was keeping you from moving with the Earth was Earth's gravity. Okay, but eventually when you float up high enough, so you keep floating, you're not being pulled by Earth's gravity as much anymore, you keep floating and you're floating, you're just flying up straight. Eventually you fly up high enough where you're no longer affected by Earth's gravity. Okay, so you just end up floating there. Okay, so in this scenario, even though the Earth is moving eastward, you are now moving westward, in contrast to earlier when you were walking with and against. You were still moving east because the Earth was rotating east, but you now that you are flying above the Earth's gravity, so it no longer has an effect on you. In the Earth's eyes, you're actually moving westward while it's rotating eastward. Pretty confusing, right? So earlier, what it's called is kind of the Coriolis force, where because the Earth is moving a certain direction and pulling you along with it, you are therefore affected by its force. Okay, so now we have to talk about the effect. Okay, so we're going to go ahead and float a bit further, or pull a bit further away so we can see this happen. What you're going to do is, as a superhero that can fly, you're going to fly towards the North Pole. Okay, but you're just going to fly in a straight line, and you're going to see what happens is we're going to mark each destination you reach. Okay, because even though you fly in a straight line, what happens is in the Earth's eyes, you've actually traveled further, and that's because the Earth keeps rotating, right? And as you fly up north, you move slower and slower until you come to a full stop. And this is because when you're being pulled by the rotation of the Earth on its equator, that's where you're moving the fastest, okay? Because the circumference of the Earth's equator is, since it's the center of the Earth, it's the largest part, it's the largest circle. Whereas if you were to move parallel, in a parallel line and cut the circumferences, right? Each circumference gradually gets smaller, okay? And the formula for speed is distance over time, right? So on the equator, you get more distance in the same amount of time as you would on a higher portion next to the North Pole, until eventually you reach the center of the North Pole. Okay, and at the North Pole, you'd basically just be standing still. You wouldn't be moving at all. So that's the only part where Coriolis force doesn't affect you. Okay, so this time, in order to actually fly a straight line up to the North Pole, what you'd have to do is move as fast as you would be if you were standing on the equator, and then gradually slow down. So there you see that you were able to stay on the line. Interestingly, right, so let's go ahead and pull out some more. Interestingly, if you go as fast as you are, if you go at the speed of the equator, you see that you're still staying with that line, right? But as you get closer to the North Pole, so you pass the line, but you're still staying at the same speed as you are from the equator. As you go closer to the pole, each time you get closer, you're actually moving faster and faster and faster. Okay, and that is the essence of the Coriolis effect. So you make it to the center of the Earth, and now you don't move as much. That is basically the essence of Coriolis effect. Your speed is relative to that of the Earth's movement. Okay, so the next topic is going to be prevailing winds. Okay, so as I mentioned earlier, the Earth rotates in an eastward motion. Okay, and air is basically just floating around us, right? So it's not exactly touching Earth, it's just held near Earth due to gravity, right? But as we saw in the scenario where we were a superhero, as we float up, we're kind of being left behind by the Earth's movement. Okay, so this is the first we're going to see wind. This is the first scenario where we're going to see wind actually happen. The air is being left behind, which means that it's moving westward. Okay, So even though the Earth is rotating eastward, since the air is just floating and being left behind, air is technically moving westward. Okay, but now we're going to add another factor, and that is the heat of the sun. Okay, so let's go ahead and zoom in. So Earth is moving eastward, right? And now we have air moving westward, and this is creating initial wind movement. Okay, but we have the heat of the sun. Okay, and it's heating up the surface of the Earth. Okay, so where it's hottest is what we'll call the tropical zone. All right, and as it heats up the surface of the Earth, it also heats up the gas molecules, making that particular area become low pressure. Okay, so where the sun is concentrated the most is where it's hottest, the tropical zone, and that area becomes a low pressure area, and this forces the gas molecules to kind of go into the rise up, because they become less dense. They rise up and they move towards the poles because it's cooler. That means there's more space for them to invade, and they start moving towards the poles. And since they start moving towards the poles, technically that means that they're moving faster, because at first they were moving at a speed that's being pulled by the equator. As they get closer to the poles, they're moving at that same speed, so now they're moving faster. Okay, and they begin to cool down and they begin to drop, and this makes a subtropical zone. Okay, and that area is
high pressure.
So now we have a
high pressure
area because the gas molecules are being pushed down because they're being cooled down. Okay, and as I mentioned earlier, what they do is they push out the gas molecules that inhabit the area towards the space where gas molecules are leaving the area. Okay, and that actually makes the winds slow down as they move towards the equator again, and this forms what we call the trade winds. Right, now these particular vertexes are called the Hadley cells. Right, now they're basically just named by scientists. I don't know much about that, you'll have to research it. Now let's go ahead and move to the polar zones, okay? Because the polar zones are the most naturally occurring winds that's gonna affect the Earth. Why? Because they're not as affected by the sun. They barely get any sunlight, if at all, and that makes it extremely cold up there. So gravity is definitely pulling down all of the gas molecules. That means that the area is a high pressure area, and they have to go to a low pressure area, which means anywhere else is low pressure by default because they're the coldest and they got most of the pressure just on them, right? Okay, so this new low pressure area is what we call a subpolar zone. Okay, and from the Hadley cell we also get gases being pulled to the low pressure area from there, but not as much as from the polar zone, right? And as they move towards the pole, once again the winds get faster, and these are what we call the westerlies. Okay, so they're called westerlies because they come in from the west moving towards the east, right? So just make that clear. The westerlies are mostly found in temperate zone areas. Okay, as both high pressure areas push towards the low pressure area, it kind of causes a convergence where it has to push up. Okay, and since it's low pressure, that also means it's different from the effect of the sun. So that low pressure is because of heat. In this instance, it's mostly because it's being pushed out, right? So even though gas molecules can't move, when there becomes an abundance of them, they kind of just pile on and push them out. And then the other one is from the original low pressure from the tropical zone and subtropical zone, or high pressure. Okay, so in the polar zones, this creates the polar cell. Okay, as they move back towards the north and south poles, right? And this causes winds known as polar easterlies. Okay, so the polar easterlies and westerlies are just consistently moving in the direction that they're named, right? The easterlies consistently moved from east to west. The westerlies consistently moved to west, from west to east. Okay, and finally the other cell that's created is the Ferrel cell. So we have from the equator we have going towards the poles, just 3 different types of cells. Okay, these are 3 vertexes. Okay, so in total we have 6 since we have both hemispheres. Another thing I'd like to note is the Earth rotates around its axis, which is roughly, I believe, 23.45 degrees. You'll have to double check that, but I think it's 23.45 degrees. Okay, and it does rotate on its, the sun's heat does affect the equator, which is the center, right? This is called an equinox when it's directly on the equator. And we have the summer and winter equinoxes, right? When it's on its upper angle, it's affecting the Tropic of Cancer, and when it's on the lower angle, it's the Tropic of Capricorn, and those are called the solstices. Okay, and just the same, you have your summer and winter solstice. All right, so to have a better idea of what's going on, here's a 3D representation. So we have our equator, we have our west side, our east side, and we have our mid zone and polar zone, right? We have our temperate and polar zones. Okay, and we'll have this dotted line for reference of the, like, being a straight line. Okay, so let's start with the polar zone. It's cold up there, high density, everything, high pressure, right? Pushes towards a low pressure area, and as it gets there, it gets pushed up by divergence, right? So low pressure, and then it goes back to the pole, to this scenario, the South Pole, right? Then we go back here to the sun, warms up the area,
low pressure.
Then we see it go to a cooler area, go to a cooler zone. The gas molecules move to a cooler zone, which is making it move faster eastward. And then it falls back to our high pressure zone, falls down and goes back. So these lower ones, that's why we have the trade winds and the westerlies, because we're not basing them on the winds that are above, because they don't really affect us that much. Okay, those are what makes the trade winds, right? Okay, and then we have at the Ferrel cell, high pressure gets pushed down, then the wind moves towards the polar area, it starts to get faster. These are called the westerlies. Then we have the complete rotation, completing the Ferrel cell. Okay, so that's a 3D representation of what I was trying to explain earlier. Now, let's move on to, so what we're going to see here is we flattened out we have the world map basically. So let's go ahead and put a compass so we know which way is which. We'll start with the equator. So that starts making our tropical zone into our subtropical zones, which is the start of Tropic of Cancer and Tropic of Capricorn. Okay, which goes into our temperate zones, going into our Arctic and Antarctic circles, and subpolar zones and polar zones. Okay, and then we have the basic winds that are running along the Earth. We have the trade winds, which create the intertropical convergence zone, so that's where the winds kind of meet. And then we have our westerlies, winds that are going from west to east, and we have our easterlies. Okay, and the last thing we have to consider is the axis of the Earth. Okay, so the axis, the rotation of the Earth on its axis around the sun is what makes our year, right? So on the bottom you have my little calendar tracker, and you're going to see what happens throughout the year. Okay, so this is how the winds would move throughout the year. There's a reason the trade winds aren't called easterlies also, because, so if you notice, the trade winds actually move above and below the equator. So there's a problem with this representation. It doesn't show you what happens to the winds that are moving towards the equator, then moving away from the equator, because of Coriolis effect. So we're actually going to modify this. Okay, start over. So we have the pattern, right? We have the normal pattern, but actually you'll see at the trade winds, the point of trade winds, they actually move backwards, or back and forth between east and west. which is pretty cool. And that's why they're not just called easterlies, because they don't just go from east to west. They actually, since they move up and down the equator, they move east and west depending on the time of the year. Okay, so that's pretty neat. What we're gonna do now is we're gonna like look at a place that's affected by this, and that's my native country, the Philippines. Okay, so let's go ahead and zoom in so we have a better view. Right, we have our compass again, and we have the Philippines is right above the equator and right below the Tropic of Cancer. So we can see we have our tropical zone and subtropical zone, and I'll show you how throughout the year winds affect the Philippines. Okay, so we have our normal trade winds, which are going westward along the equator. Okay, and we move up and down because of the axis of the Earth while it's rotating around the sun. And you'll see here that the winds shift, right? You go all the way down, they come back up. So starting somewhere around here in April, it's going from the northeast to the southwest, to summer where it's going southwest to northeast, and these will create our consistent winds for the Philippines. Okay, let's go ahead and reset this example. There, so we have those winds, right? Those winds create the southwest monsoon, also known as the Habagat. Okay, hanging Habagat. And then from above, we have the northeast monsoon, which is hanging Amihan. So we have Habagat and Amihan. Bayan. And it's really cool seeing them in motion with the calendar at the bottom, right? So we can see here, by the time it reaches September, October, the northeast winds start coming down. Amihan starts falling on the Philippines, and those are the winter months. So those winds are technically supposed to be colder, right? And as we go into the summer months, starting around April, May, we have Habagat just pushing upward, and that's when it becomes hotter. And because of this, it kind of creates a strange scenario of how winds affect countries that are in these zones, right? But overall, they only affect certain areas. So I'm going to go a bit off topic here. So when I was studying in the Philippines, about architecture, when we got to the tropical part, none of my teachers could actually explain why the wind was like that. I don't know if they actually understood it and just didn't know how to explain it. So I had to learn all of this by myself. And the interesting thing is we had to apply the idea of hanging Amihan and hanging Habagat on all of our projects, right? But we also do site inspections during college, and wind does not affect everywhere, right? Like in order for you to actually feel the presence of wind, it has to be at least moving above 15 kilometers per hour. Otherwise, it just feels like, really heavy days. There's especially being around the tropical zone, it's just really hot, right? So off the record, I'd say that this information is only useful for certain projects, like especially in in the Metro Manila area. The only thing that this can help you with is like understanding where rain is coming from. So you can kind of assume that during these months, from May to September, you'll have rains coming in from the southwest, and not as much rain coming from the northeast during the winter months. But you'll also understand like how cyclones form and go over the Philippines. But overall, I don't know, I never really found it helpful to put these representations for our projects, because they don't really explain much and it only affects certain areas. So I'll talk about that in another video, and I'll also talk about like factors that also affect wind. But in the overall scheme of things, I would still say that doing site inspections will help you more with determining how you should set up your windows and doors on your projects, because just putting the arrows on your projects doesn't really mean anything. But anyway, that's where I'm going to end this video. It's a bit long, but I hope you did learn a lot. I hope you guys always take care. I hope we can always better ourselves, and until next time, bye.